Hello everyone, welcome back to Knowledge Bytes. Have you ever wondered how AI predicts the next words while you are typing? Understands spoken language? Remember earlier part of the sentence? Traditional neural network process information one piece at a time, but they don't remember what came before. Real world problem requires memory and context. That's exactly why recurrent neural network or RNNs were created. In today's episode, we will explore how RNNs work, how they were revolutionary, where they struggle, and how they paved the way of the modern AI systems like ChatGPT. Let's dive in. Why sequence data matters. Not all data is independent. Consider a sentence. If I say, the cat sat on the, you can probably predict the next word because you remember the word that came before. The same principle applies to the speech recognition, machine translation, stock market forecasting, and sensor monitoring. In these examples, the order of the information matters. This type of information is called sequential data. To understand the sequential data, AI needs memory, and that's where RNNs comes into the play. Problem with the traditional neural network. Traditional neural network process each input independently. Imagine reading a book where every page is disconnected from the previous page. The story wouldn't make much sense, right? Similarly, a traditional forward neural network cannot remember previous inputs. It only sees the what's current in front of it. This became the major limitations when working with the language or speech or time series data, where context is critical. To solve this challenge, researchers needed a network that could remember the past. What is RNN? A recurrent neural network, RNN, is a type of neural networks especially designed for the sequential data. Unlike traditional neural network, RNN have a built-in memory mechanism. They process information one step at a time while carrying knowledge from the previous steps forward. Think of it like reading a sentence word by word while remembering everything you have already read. This ability to maintain the context made RNNs one of the earliest breakthroughs in the sequential modeling. What makes a RNN different? The key information behind the RNN is something called the hidden state. The hidden state acts like a network memory. At every step, the network receives two things: the current input, the information remembered from the previous step. It combines together to generate an output and update its memory. This cycle repeats continuously throughout the sequence. As a result, the network can learn relationships that span across multiple time steps. Understanding the hidden state. Think of the hidden state as a notebook that travels through time. Every time the network sees new information, it writes important details into the notebook. Okay, the notebook then processes to the next step. So the more input arrives, the notebook gets updated and it's updated again and again, and it processes to the next input. This allows the neural network to retain context and make decisions based on the both current and the past information. Without the hidden state, RNN would have just like a normal traditional neural network. So, information flow through time. Let's see how information flows through an RNN. Imagine the sentence, I love learning A. The word I enters first. The network creates an initial hidden state. Next comes the word love. The network combines the network combines a new word with the information remembered from the previous step. So the same process continues with the learning and this AI. So at every step, the hidden state involves and accumulate the context. By the end of the sentence, the network has built an understanding the entire sequence. So now, why it's called recurrent? The word recurrent comes from the repeating structure inside the network. The same neural network is reused at every time step. Instead of creating separate network for every word, the network repeatedly applies the same set of weights. This creates a loop of information following through time. That hidden states continuously feeds information from one step to the next step. That's why they are called the recurrent neural network. So understand the real world application. RNNs became popular because many real world problems involve sequence. In natural language processing, RNNs were used for the language modeling, sentimental analysis, and text generation. In speech recognition system, they helped converting spoken words to the text. For machine translation, they enable the translation between languages. And in finance, RNNs were used for the stock markets, forecasting, and trend predictions. They also found they also found applications in the handwriting recognitions, video analysis, and predictive typing. Wherever sequence data exists, RNNs can prove valuable insights. Now, the memory problem. Although RNNs introduced memory, they still faced an important challenge. Their memory is limited. The sequence becomes longer, information for earlier time steps gradually faded out. Imagine trying to remember the first sentence of the very long paragraph, right? So, further back the information is, the harder it becomes to retain. RNNs experienced a similar issue. They perform well on short sequence but struggle with the long-term memory. This became known as the long-term dependency problem. So now let's understand the vanishing guardian problem. One of the main reasons for this limitation is called the vanishing guardian problem. During training, neural networks learn through the process called back propagation. The learning signals travel backward through the network to adjust the weights, right? In long sequences, this signal becomes smaller and smaller as it moves backwards through the time. Eventually, it becomes so tiny that network can no longer learn effectively from the earlier information. So as a result, important context is often forgotten. This makes learning long range relationship extremely difficult, right? So now let's understand the long term dependency problem. Let's consider a simple example. Suppose we have the sentence like, John went to the store and bought some milk. He is. To predict who he is refers to, the network must remember the name John appears much earlier in the sentence, right? Human can easily make this connection. However, traditional RNN often struggle because the relevant information occurred many times in the step earlier, right? This challenge is extremely what we mean by the long-term dependency. So now, the birth of the LSTM. To solve these limitations, researchers developed a long short-term memory network that is known as LSTM. LSTM introduced specialized memory cells and gates. These mechanisms allow the network to decide this information, what informations to keep, what informations to forget, what informations to output. This dramatically improves the network ability to retain the information across long sentences. LSTMs became one of the most important advanced in the deep learning. We will explore them in more details in the next episode. Now, understand the RNN versus transformers. Today, most states of the artificial AI systems use transformers instead of the traditional RNNs. RNNs process information sequentially, one step at a time. Transformer process entire sequence simultaneously using the attention mechanism. We will learn more about the attention mechanism in upcoming videos. This allows transformers to capture long-term dependencies for the most effectively. Large language models like ChatGPT are built on the transformers architectures. However, RNNs remains historical importance because they introduced the core idea of the sequence modeling that inspired everything that followed. Key takeaways. Let's quickly recap what we learned today. RNNs were designed for the sequential data. They introduced memory through hidden states. This enables AI systems to understand the context across time. RNNs power early breakthrough in language processing, speech recognition, and sequence predictions. However, they struggle with the long-term dependency because of the limited memory and the vanishing guardian problem. These challenges led to the development of LSTMs and eventually transformers. Understanding RNNs helps us understand the evaluation of the modern AI. Now let's understand AWS Exam Corner. Before we wrap up today, here is a quick AWS exam tip. Remember these key points. RNNs process sequential data one step at a time. Their major limitations is the vanishing gradient problem. LSTM solve this issue using memory cells and gates. Transformer uses attention mechanism and have largely replaced RNNs in modern AI systems. For certification exams, focus on understanding when to use the RNNs, LSTMs, and transformers based on the problem requirements. Now, and that brings us to the end of this episode, and we have explored how RNNs introduce memory into the neural networks, how they process the sequential information, and why they became the foundation technology in the artificial intelligence. In the next episode, we will dive deeper into the long and short-term memory networks, or LSTMs, and discover how they overcome the limitation of the traditional RNNs. If you found this episode is helpful, please like, share, subscribe to the Knowledge Bytes. Until next time, keep learning, keep growing, and remember, learn something new one byte at a time. Thank you.